Do you remember that Christmas where you saw a nephew, a niece, a younger child open that present, that gift? Maybe it was just a special day. And what was before them but this wonderful figure? It seemed to be a million toys in one. You'd pull an arm off and move it over here and attach it in a different place and remove the leg and move them over somewhere else, and suddenly it was a truck. Change was the key. Welcome to the world of transformations. A change in an object. Maybe its size. Maybe its position. Maybe it's, well, I wonder what it could be. One of the ways a transformation can occur is known as a rotation. What would this look like? Well, here's a simple right angle triangle. At least it appears to be a right angle. Until you see a perpendicular intersection, you can't call it a right angle triangle. So we'll just call this one a triangle. If we take this triangle and rotate it, we will be then turning it around an axis. Our triangle right now is rotating in a clockwise direction. How far? We went 360 degrees. So 360 degrees clockwise is certainly one way that a triangle could be rotated. But we all know not everything goes in a clockwise direction. How is our triangle moving now? Yes, I can't get anything past you. We were now moving in a counterclockwise direction. Each of our triangles moved in a full circle. We seem to arrive back at the same spot. One was a clockwise direction, the other was a counterclockwise direction. Did you notice what point didn't seem to move? Yes, it was somewhere around the middle of the hypotenuse. This point would then be known as the center of dilatation. We could choose any point on the triangle or even a point somewhere else on the screen and use it as a center of rotation, as long as the coordinates, in this case, A, B, C, remain the same distance away. At all times, we would create a rotation. Another type of transformation that can be examined is called a translation. We enjoyed these as young children, and maybe you still do today. You got on top that slide and you slid down the slide, moving you from point A to point B. You were still the same person. You were still the same size. Take, for instance, our lovely triangle again. One could move this triangle to the right and down. We have now translated the triangle so many units to the right and so many units down. Not only did we do that to A, but we also did it to B, and we also did it to C. Each corresponding point moved in the same manner, to the right and down. When we're working with triangles, the original or starting figure might be referred to as the original figure. This original figure produces a picture, much like you saw in the morning when you looked in the mirror. You saw a reflection of yourself, but we'll get to that in a moment. We're still talking about translations. So the image is the resulting figure. We have a special way of naming those coordinates, those vertices. It used to be called A. Now, since it's the image, it will be called A prime. Notice the top right-hand corner. Kind of looks like an exponent. It's not, but it kind of looks like one. We know this point to be called A prime. In the bottom left-hand corner, what do you think you would call this point? Well, a couple questions to consider. What did we call it before? Is it an image? Yes, I can't get anything by you guys. You're absolutely correct. It's B prime. Who's left? Again, You're way too quick for me today. C prime. We have now translated the original triangle ABC to the right and down, producing triangle A prime, B prime, C prime. Only location changed. Transformations can also be reflections. I mentioned this a moment ago when I said you woke up in the morning and you looked in the mirror and you saw a reflection. I wonder what the reflection of this triangle would look like. Why don't you take a moment to try to produce what you think will be the reflection of the triangle if we set a mirror, let's use this red line, in this position, and we reflected the triangle over the mirror. We call this reflecting over a vertical line. Can you draw the image? Give it a try. Some of you may have come up with a figure like this. If you did, reach behind, give yourself a pat on the back. Good job. If not, there'll always be another time to try. I guess that's why we're here, to learn. There's a couple things that's special about this triangle, though. If we started off with point A in the bottom right-hand corner, where would A prime be? It would be over here in the bottom left-hand corner. Notice, right became left. We have an opposite orientation occurring. The distance from A to the mirror must remain the same as the distance from A prime to the mirror. We often see on figures little slashes like this indicating the distances are the same. There's B. Well, I'm going to decide that B was sitting right up here on top of the mirror. I wonder where B prime is. Well, since B was touching the mirror, I guess B prime has to be touching the mirror. And that's why it's really hard to tell the difference. They're actually occupying the same spot. They're sitting right here up against the mirror. Again, the same distance from the mirror. This would be known as a mirror image or reflection. Again, we've been folding over a vertical line. I guess another way to think about a reflection is just like a fold on a piece of paper. What could you call this red line? We called it a mirror. What could be its other names? Can you think of any? Line of symmetry. Good job. It's a line of symmetry, a line of reflection, or a mirror. Finally, the fourth and last transformation that we'll take a look at is called a dilatation. If we stop and think like a language arts teacher here, what would this word be if we remove the suffix? What would this word be, possibly anyways, if we were looking at the root of this word? D-I-L-A-T-A-T. It was probably an E. Dilatate. Dilate. I think our eyes often dilate. They get bigger or smaller. Kind of gives us a little bit of a hint at what dilatation might mean. Let's take a look at a dilatation. Well, we're back to looking at our good old right angle triangle. And we're going to watch what this triangle is about to do. Oh, that triangle's growing. Can you describe how that triangle grew? You're correct. It grew proportionately. If this triangle originally was 3 units and now it's 9 units, how many times bigger did our triangle get? Or at least, how many times longer is the vertical line? Correct, 3 times longer. But when I say proportional increases, catch that. Proportional increases. If it grows vertically at a rate of, or factor of 3, it has to do the same thing horizontally. So if this was 2, which wouldn't make a lot of sense in this picture, bad example, I guess, because it looks like it's longer than it is wider, so that wouldn't be a very good number, would it? It's often a good idea to make our examples resemble reality. So let's make it a 5. If it's 5 originally, and it has to grow proportionately, how long would the bottom of the triangle, the big triangle, be? If I placed a variable here, what might x be? Right, proportional increases, meaning factor of 3 vertically, factor of 3 horizontally. So this x must now be 5 times 3, or 15 units. Now we have proportional increases. If we went from the top vertex and called it A, and calling the original, the small one, the small triangle, and the image, the big triangle, I wonder what it would be called. Let's remove these numbers for a moment to make things a little bit easier to see. Did our image get bigger or did our image get smaller? Well, definitely it got bigger. And what would a photocopier call that? You're right. If we make things grow, if we make things get bigger, we are enlarging the figure. And of course, the opposite of that would be where we would make it smaller, or what often was called a reduction. Let's go back to our image and original notation that we talked about before. If we called the point in the bottom left-hand corner of the original B, what would we call the bottom in the image? We would now call it B prime. You're correct. You guys are right on the ball today. I'm impressed. At the bottom of our hypotenuse, if this was a right angle triangle and I called it C prime, what would this other point be? This last point that we don't know, located right here. Here's a fancy word for you. Corresponds. Kind of like saying matching. So our question mark corresponds or matches with C prime. So we'll call our question mark C. Where's A prime? I don't seem to see A prime. Well, it's hiding right underneath A. This point, A, didn't seem to move. So our point A was referred to as the center of dilatation. The point that our triangle grew from. So A prime is right underneath A. We could call that coinciding. So that point, or vertex A, is also known as A prime if we're talking about the image. What was this called? Dilatations. Transformations can be kind of interesting. They're all over us. They're all around us. And we see the reflections in the morning when we get up and check out the mirror. We see the dilatations when a paramedic arrives at the scene of an accident, or we go see a doctor and they want to see if we had a head injury. They'll shine a light in our eyes. They'll be looking for dilatation, proportional changes in our eyes. Can you make a list of where we might see transformations? I think you can. You look like a pretty bright group. So let's embark on our first activity. Make a list of all the different possible transformations and where they exist and why they exist. Have a great day.